All right, let's dive into the really fascinating world of materials science. We're going to talk about how all the stuff around us actually works, and maybe more importantly, how it breaks.
I mean, have you ever really thought about this? You can take a paper clip and just bend it back and forth, no problem. But try that with a pane of glass. Yeah, it just shatters. They're both solid, right? So what gives? Well, it turns out every single material has its own secret language, and that language dictates exactly how it's going to behave. And guess what? By the time we're done here, you're going to be able to read that language too. We're going to decode all the properties that make something strong or weak or flexible or brittle, all by looking at how it responds when you push it, pull it, and stress it out.
So let's get right into it. How do we learn these secrets? Well, a lot of the time, engineers they have to break stuff. But it's not just random smashing. They do it in a really precise, super controlled way, using something called the ultimate stretch test. This right here is the tension test. It's pretty straightforward, really. Engineers take a standard-sized sample of a material, kind of like the one you're looking at. They clamp it into a machine, and then they just pull. They pull on it from both ends until it snaps right in two. And the whole time, they are measuring every single thing that happens to that material as it stretches. And all that data they collect, it creates this completely unique fingerprint for that material. We call it a stress-strain curve, and honestly, it is the key. It unlocks pretty much everything we need to know about a material's personality. And this is what it looks like. Think of this graph as our Rosetta Stone. On the vertical axis, you've got stress. That's basically just how much force you're pulling with. And on the horizontal axis, you have strain, which is how much the material has stretched. The really important thing to get is that this curve, it tells a story from beginning to end. Okay, so this story starts right here, in this perfectly straight part of the line. This is what we call the elastic region. If you're pulling on the material and you stop anywhere along this line, it'll snap right back to its original shape, exactly like a rubber band. And the steeper this line is, the stiffer the material is. But if you keep pulling, you're going to hit this point. It's called the yield strength. And this is the point of no return. Seriously, any stretching that happens after this point is permanent. You have now changed the material's shape forever. This is exactly what's happening when you bend a paperclip just a little too far and it stays bent. So we keep pulling and we reach the very top of the curve. This peak is its ultimate tensile strength. It's the absolute maximum stress the material can handle before it starts to give up and get weaker. And right around this point, something interesting happens. You'll see a little thin spot start to form, which we call a neck. That's the signal that the end is near. And finally, just look at how far the curve stretches sideways before it finally breaks. That tells us all about its ductility. A really ductile material can stretch a ton before it snaps. Think of pulling taffy or stretching out a copper wire. A material that isn't ductile, well, it just can't do that. And this is just the perfect way to see the difference. Look on the left. That's a ductile material, maybe like copper. It's got this long, stretched out curve. It bends, it deforms. It gives you plenty of warning that it's about to fail. Now look at the right. That's a brittle material, like chalk or glass. The curve is short and steep. It just takes the stress, and then snap. It's gone. Zero warning. Okay, so that's what happens when you pull on something. But let's build on that, because in the real world, things aren't just getting stretched, right? They're also being squashed and twisted and dented all the time. So where tension pulls a material thin, compression does the opposite. It squishes it. And as you can see, a ductile material doesn't just get shorter, it kind of bulges out in the middle. We call that barreling. Brittle materials, though, they tend to just crumble and fracture when you squash them. And then, of course, there's hardness. This one's pretty simple. Hardness is just a material's ability to resist getting dented or scratched. And it's a super practical property because it's a really quick and easy way to get a feel for a material's overall strength and how well it'll hold up to wear and tear. And yeah, you guessed it, there's not just one way to measure hardness. It really depends on what you're testing. Engineers use all sorts of different shaped indenters, everything from little steel balls to super sharp diamond pyramids, to basically poke the material and see what kind of dent it leaves. Like, the coupe test uses this tiny, long pyramid shape, which is just perfect for testing something really thin or brittle, like a piece of ceramic. So this machine here is a Rockwell hardness tester. It's one of the most common ones you'll see. It works by very precisely pushing one of those indenters into the material with an exact amount of force.
Then it measures the depth of the mark it leaves behind and gives you a hardness number. It's a really fast, super reliable way to check the quality of a part.
Okay, so we've got a pretty good handle on how materials react to a single push or a single pull. But what happens over time? What about repeated stress over and over again? Well, this is where things can get really, really dangerous. We're talking about fatigue, and it's the exact reason why that paper clip you bend back and forth eventually snaps. See, each time you bend it, you're creating tiny, microscopic cracks. And with every single bend, those cracks get a little bigger. And here's the scary part. The force you're using is way below what it would take to break it in one go. But eventually, those little cracks link up, and the whole thing fails all at once. Then there's fatigue's slow-motion cousin, creep. This is another one that happens over time. It's the slow, gradual sagging of a material that's under a constant load. The perfect example is a bookshelf that's been holding heavy books for years and starts to bow in the middle. For metals, this becomes a huge deal when things get hot, like inside a jet engine. Okay, let's put all of this together, because now we get to the really cool part. By looking at the surface of a broken piece of material, what we call the fracture surface, you can actually become a detective and read the entire story of exactly how and why it failed. Just look at the difference here. It's amazing. On the left, you've got a ductile fracture. See how it's all rough and dimpled? That surface is telling you a story about tiny little voids that formed inside, grew bigger, and then slowly linked up until the whole thing tore apart. But on the right, that's a brittle fracture. It's sharp, it's clean, almost like a crystal. Those are called cleavage planes, and it's where the atomic bonds just snapped suddenly right along the material's crystal structure. They're telling two completely different stories. And believe me, that difference is absolutely critical in the real world. A ductile failure, it gives you a warning. The material stretches, it gets thin, you can see it deforming. But a brittle fracture, it is sudden, it is catastrophic, and it happens with absolutely no warning. So what about fatigue? Oh, its story is maybe the most fascinating of all. A fatigue fracture has these really distinct patterns on it that look just like ripples on a sandy beach. And each one of those beach marks shows you how far the crack grew over a period of time. A forensic engineer can look at a surface like this and literally read the entire life story of the failure, from the very first tiny crack all the way to the final catastrophic break. So there you have it. By understanding these basic tests and the ways things break, we've basically learned how to decode that secret language of the materials that build our entire world. And knowing this language is what lets us design safer airplanes, stronger buildings, and products that you can actually rely on. So the only question left is, what new secrets, what new languages will the materials of tomorrow reveal to us?